Hello everyone. Now we'll see how to conduct QPSK experiment using MATLAB Simulink tool. QPSK or quadrature phase shift keying is a digital modulation technique which represents data using 4 different phase values. So it transmits 2 bits per symbol. So here die bits are used. So 0, 0, 0, 1, 1, 0 and 1, 1. So 4 different symbols are possible here. So compared to binary phase shift keying, this QPSK is a bandwidth efficient method. So here to simulate this experiment or to conduct QPSK modulation experiment, first we have to open MATLAB software. So this is a MATLAB window. Next select the Simulink library. So open Simulink block library with this. So click on this. So we get a new browser window. This is called as Simulink library browser. Once this is open, now we have to create new model. So select new model. Once this is open, now we have to create new model. So select new model. And this is blank. Okay, this is the blank area. So once we select that new model, this blank model will be open. So here we have blank area. And here we have to build our model. So for our model, different blocks are required. We can fetch those blocks from the library. So to add components to this blank model, select this library browser. So this is the library browser, and from here we have to add the components. For example, in our model, QPSK modulator, first block required is the source. That source is available in the communication system toolbox. So select this communication system toolbox. Inside this we have communication sources. So select this, and random data sources. So inside this random data sources, we have a required block which is called as random integer generator. So right click and add block to model untitled 1. Once it is added, now we get that component in our, okay. Once that block is added to the model, it is available here. So random integer generator is the very first block which is required in our modulator. So once this required block or component is added, then we can set the parameter depending on our requirement. To set the parameter, double click on this. Now we get this dialog box. Here we can set the source parameter. By default, M-array number is 8. Since we have only 4 die bits, here we can set this as 4. So 4 integers like 0, 1, 2 and 3 are generated, and then we can map it to corresponding binaries. Next, here we can set initial seed depending on our required pattern, and also we can set the sample time. Next, select OK. This is how block parameter or property of this random integer generator is set. Similarly, we can add the remaining blocks to our model, and we can interconnect it. After setting the parameter, we can simulate and we can get the result. So this is the method in Simulink. So this model, it represents our QPSK modulator, and this random integer generator is the source. The output of this random integer generator is in the form of integer value 0, 1, 2 and 3. Then we have to modulate it using QPSK modulator baseband. So this QPSK modulator baseband, it converts those integers into complex numbers. The output of this QPSK modulator baseband is in the form of plus or minus A plus or minus JB. So plus A plus B plus A minus B minus A plus B and minus A minus B. So 4 different values we get at the output of this QPSK modulator baseband. Next, we have to separate real and imaginary part of the complex number, which gives odd and even bit sequences. So this complex to real imaginary, this block is used to convert complex number into real and imaginary parts. So at the output of this complex to real imaginary part, here we get odd sequence or real sequence, and here we get even sequence. So this real or odd sequence is modulated using cos wave as a carrier, and imaginary or even sequence, it is modulated using sine wave as a carrier. Once we get binary phase shift keying or BPSK wave at the output of this product 1 and product 2, we have to combine it. To combine these two individual BPSK, we are using adder. So this resultant signal at the output of adder represents QPSK. So this is the overall block diagram explanation. So once this model is ready, now we have to set the parameters of each block. First, double click on random integer generator, set M-array number as 4, initial seed 63, and sample time as 0.1. With sample time 0.1, we get 10 integers per second. And with M-array number equal to 4, we get 0, 1, 2, 3. These 4 integers as output of random integer generator. Next, set QPSK modulator baseband parameter, double click. So here set phase offset as pi by 4. If phase offset is 0 here, then we get 0, 90 degree, 180 degree and 270 degree as phase values. If phase offset is pi by 4, then we get 45 degree, 135 degree, 225 and 315 as 4 different phase values, which represents the die bit. Next, select constellation ordering as gray. Next, input type as integer. Let us see what is the constellation for this. So for our set parameter, this is the resultant constellation. So this is 0. So in the first quadrant, we have message point 0. In the second quadrant, message point 1. Next, message point 2 is in the fourth quadrant and message point 3 is in the third quadrant. So this integer 0 is represented as 1, 1 in binary. Integer value 1 is represented as 0, 1. Integer 2 is represented as 1, 0 and integer 3 is represented as 0, 0. So we have chosen gray code here. Next, set the parameter by selecting OK. Next, we have to set parameters of the carriers. So this block generates the carrier required for the in-phase channel, and this block, this generates the carrier required for the quadrature channel. So cos wave is a carrier used in the in-phase channel, and sine wave is a carrier used in the quadrature channel. So select this block. So for cos wave, amplitude is 5 volt. Frequency in terms of radian per second is 80 pi. So the linear frequency will be 80 pi divided by 2 pi. So 40 hertz is the carrier frequency here. Initial phase is pi by 2 because it is a cos wave. Sample time is very small, so it is 1 by 10,000. Similarly, set the parameter of a quadrature carrier. Again, here amplitude is same as the in-phase carrier, so it is 5 volt. Bias is 0. Frequency is same, 80 pi. But initial phase is 0 because it is a sine wave, 0 phase. Sample time is 1 by 10,000, very small sample time. So all the parameters are set now. Once parameters are set, now let us simulate this with total simulation time as 1 second. So run the model. So as we can see here, this is the constellation diagram. In this constellation diagram, this first quadrant point, this represents 0, and this second quadrant point represents 1, and fourth quadrant point, this represents 2, and this represents 3. So this is pi by 4, and this is 3 pi by 4, and this is 5 pi by 4, and this is 7 pi by 4. So these are the 4 different phases. Next, let us see the waveform. Okay, so this is the output. Here, first waveform, this represents output of random integer generator. So this is integer value 1, this is 0, 2, 0, 2, and this is also 2, next 2, 0, 1, 3. So 0, 1, 2, 3 are all 4 integers are generated at the output of random integer generator. This second waveform, it represents odd sequence, and third waveform, it represents even sequence. To understand how these odd sequence and even sequence are generated from the integer, let us consider this table. Here first column represents m array value, integer values 0, 1, 2, 3, and second column values, gray encoded bit represents binary. Here this first table, so here this first column, it represents m array value in terms of integer 0, 1, 2, 3, and second column, it represents gray encoded bit values 1, 1, 0, 1, 1, 0, and 0, 0. And the last column, third column, it represents corresponding QPSK phases. So if integer value is 0, corresponding binary value will be 1, 1. So this 1 is a odd value, and the second one is a even value. Corresponding phase will be 315. On the other hand, if integer is 1, then corresponding gray encoded bit is 0, 1. So 0 is odd bit, 1 is the even bit, and phase is 225. For integer 2, 1 is the odd bit, 0 is the even bit, and corresponding phase is 45 degree. And for integer 3, 0 is the odd bit, 0 is the even bit, corresponding phase will be 135 degree. And this second diagram, this represents the corresponding constellation diagram. Now in this waveform, here we can see that first integer is 1. So in terms of gray code, this 1 is represented as 0, 1. So odd bit is 0 and even bit is 1. Next, second integer is 0. Corresponding gray encoded values are 1 and 1. So here it is high. So 1 and here also 1. Next integer is 2. So to understand this, we have to refer our previous table. So for this 2, corresponding gray encoded values are 1, 0. So 1 is odd bit, 0 is the even bit. Next it is 0, integer 0. So 1, 1. Next again it is 2. So for 2, corresponding gray encoded values 1, 0. Next it is 1, 0. Next 1, 0. Next 1, 1. Next 0, 1. And finally 0, 0. So here integer is 3. Corresponding gray encoded value is 0, 0. As we can see in this diagram, this real sequence or odd sequence is used to modulate cos wave. So this is the in phase channel here, and this imaginary or even bit sequence, it is used to modulate sine wave in the quadrature channel. If odd bit is 0, it is represented by inverted cos or 180 degree phase shifted cos. Similarly, if odd bit is 1, it is represented by 0 degree phase shifted cos. Similarly, if even bit is 1, it is represented by 0 degree sine, and if even bit is 0, it is represented by 180 degree phase shifted sine wave. Once these two individual BPSK signals are generated in the in phase channel and quadrature channel, then we are combining it using adder. Now let us see what are the waveforms at the output of product 1 and product 2. So this shows the waveform. Here, this fourth and fifth waveform, these two waveforms represents BPSK output at the output of in-phase channel and quadrature channel. Now here, initial odd bit, this bit is 0. It is represented by minus cos. And here, odd bit is 1. It is represented by plus cos. So here phase is 0. Similarly, at this point, here there is a transition. This is 1 and this is 0. Therefore, here there is a 180-degree phase shift. So this is minus cos here. Next, if we refer that quadrature channel, initial bit is 1. It is represented by sine. Next, second bit is also 1. It is also represented by sine. So there is no phase shift here. Whereas third bit is 0. So there is a transition from 1 to 0, which is represented by minus sine. So here there is a 180-degree phase shift. Similarly, next fourth bit is 1. So here there is a 0 to 1 transition. It is represented by plus sign. So again here there is a 180-degree phase shift. So this is how individual BPSK modulated waves are generated in the in-phase and quadrature channel. Once these waveforms are generated, once these signals are generated, then we have to combine it using adder. The resultant signal is a QPSK wave. Now let us check the. So this is the resultant QPSK. As you can see here, first integer is 1, integer 1. Corresponding odd bit is 0, even bit is 1. As per our previous discussion, we have to represent it by 5 pi by 4. So this is 225 degree. So if you refer this point, with respect to cos, this is 225 degree phase shift. Next integer is 0. This is represented as 1, 1. Odd bit is 1, even bit is 1. And corresponding phase is 315 degree, 7 pi by 4. So this point, this represents 7 pi by 4 with respect to cos. Next integer is 2. So this integer 2 is represented as 1, 0. So odd bit is 1, even bit is 0. Corresponding phase is 45 degree or pi by 4 with respect to cos. So this is pi by 4. Similarly, next integer is 0. It is represented as 1, 1 in gray code. Corresponding phase is 315 degree. Next integer is 2. It is represented as 1, 0. Phase is 45 degree. Next integer is 2. It is represented as 1, 0. And corresponding phase is 45 degree. Next integer is again 2. It is represented as 1, 0. Corresponding phase is 45 degree. And next integer, here it is changed. Integer is 0. Corresponding gray code is 1, 1. Odd is 1. Even is 1. Phase value is 315. So this is 315 degree. Next integer is 1. Corresponding gray code is 0, 1. And phase value is 5 pi by 4 or 225 degree. Next, last integer. This is 3 here. It is represented as 0, 0 in gray code. Odd bit 0, even bit 0. And corresponding phase is 3 pi by 4 or 135 degree. So this is how each integer is mapped into corresponding gray code, and then it is represented using 4 different phases: 45 degree, 135 degree, 225 and 315. So this last waveform, it represents QPSK, quadrature phase shift keying modulated signal with 4 different phases. So this is about QPSK modulation using Simulink tool. Thank you.